Relativity. In this video, we'll be talking about relativity, and it's one of the first videos with no equations, just concepts. In classical physics, time, length, and mass are absolute quantities, meaning, for example, if we measure the mass of an object to be 1.0 kilograms, that's what it is, and that's what we use in our formulas. In problems where we're talking about objects at low speeds, classical physics is fine. However, when we get to really high speeds, meaning approaching the speed of light, classical physics doesn't quite explain what we observe when we're looking at these objects. So Einstein developed a theory when we're looking at objects at high speeds that accommodates what we observe in these cases. So he thought of space and time as one entity and didn't consider time, length, and mass to be absolute quantities. So you might have seen this diagram in explaining the space-time theory. Might be worth checking out a few videos on YouTube that go through animations of this to help you understand that link. However, for the Year 12 course, we don't need to know that. So before I get to the theory, firstly I'd just like to bring up a new definition, which is frames of reference. An internal frame of reference is one where Newton's laws of motion apply. So this frame of reference is either stationary or moving with the object with a constant velocity. Now, if we were looking at the motion of an object, that object may be observed differently by someone else looking at it from another alternative reference frame. I'll go into a little bit more detail about that in a couple of slides. Okay, so the theory of special relativity has two postulates. The first is that the speed of light in a vacuum is an absolute constant. And what that means is that it is the same for all reference frames. So no matter where we are, we always see the speed of light as the same value. And number two, the laws of physics are the same in all these internal reference frames. Alright, so going into a little bit more detail about the reference frames, we're going to say that the reference frame in these examples belong to a certain person. So when we're looking at the motion of an object, we measure it relative to an observer, and quantities like time and length depend on that observer. So looking at the first one up here with the train. So there's a man on a carriage on a train and a man standing outside the train as the train goes by. So from this person's point of view, or from their reference frame, the train is moving left to right at 15 meters a second. And then when they're looking at the actual person inside the train, that person will be moving at 16.2 meters a second. If we look at it from the other point of view, so we're looking at this person's reference frame now, the person on the train. From their point of view, from their reference frame, they're only moving at 1.2 meters a second. And actually, if they look outside the train at the stationary person, that person is actually moving at negative 15 meters a second. That can be a tough concept to grasp, but if you put yourself in the position of the person on the train and you're looking at the stationary person outside the train, your head would move to observe them as the train went by, suggesting that they're moving in your reference frame. So the reference frames in these scenarios, they work with classical physics. However, what Einstein predicted at the very high speeds, approaching the speed of light, is different. Going further, let's look at an example where there's an event that occurs. Two events are said to occur simultaneously if they happen at the same instance in time. However, they might not appear to occur at the same instance in time to different observers. So we've got two events that occur, event A and event B. Okay. Along this x-axis, we've got the distance, and along this y-axis is time. So you can see that we've got a few different frames of time occurring sequentially after another. In this example, we've got a green person which is on the train station platform and a blue person which is actually on the train. The events that occur are at either end of the carriage. So you can see this blue box represents this carriage, and over the course of time it shifts slightly to the right. These arrows represent the progression of the event in terms of the speed of light to when they will be observed. So for the person that's in green, they will observe both events A and B at exactly the same time because they are in the middle of the carriage position when both events occur. And you can see this happens when these two orange arrows meet at the same time for the observer. Now for the blue observer, although they also start in the middle of the carriage, they are actually on the carriage. And you can see when the events occur, the observer sees event B occurring first because that orange arrow meets them first. And then sometime later, the orange arrow from event A meets them. So for the blue observer, the events didn't happen at the same time. Now what I'd like you to do is watch this awesome video that explains what happens at very high speeds with really good animations. I'll put a link in the description below, but I think it might also appear just here and you can click it. State Einstein's two postulates on the theory of special relativity.